Alright, so for my own learning, but also maybe in case I can help someone else, I made this video for Chapter 4, all the review questions answered by me and explained verbally. Hopefully it helps. And yeah, you're probably wondering what this picture is. I don't know. It was a cool picture of atoms. I found it on Google. I thought it was cool. I don't know if atoms actually look like this. Uh, so, anyways, if you find this helpful, or you want me to make more in the future of like different chapters, I might make another one for chapter 6, but I don't know if I'll finish that in time. But yeah, just let me know, and yeah, let's start chapter 4. All right, so for this question, we have to classify them as either ionic or molecular. Now, what we do know is that when you have two nonmetals, they're going to make a molecular bond, and as soon as you add one metal, it's going to make an ionic. So for these questions, they're mostly going to ask with two elements, what's the bond between them, right? So for this one, we know that since they're both, if you look on the periodic table, right, carbon and oxygen, they are both metals. Sorry, they're both nonmetals. So this is going to be molecular, right? Then for this one, since we know that nickel is a metal, I can you should already know nickel is a metal, right? So this one's gonna be ionic, right? For this one, sodium is a metal, so we know it's gonna be ionic. And for this one, if we look them both up, right, they're both nonmetals, so this is gonna be molecular. For this one, we have to determine the empirical formula for the compound represented by each, right? So, empirical formula, what does that mean? Well, basically, that just means that you're breaking it down into the smallest pieces, right? So, this, if we have two of this and four of this, it's the same exact ratio as one of this and two of this, right? So, 2 to 4, 1, the one you don't have to write, 1 to 2, it's the same ratio. Now, if we do the same thing for each of these, this is already in its empirical formula because there's not really a ratio for these two that you can simplify it to. So this one is going to stay the same, right? And for this one, you can divide both of them by 2. So you can get C2H5. All right. So for this question, you need to determine the number of each type of atom in the formula, right? So each type of atom, right, that's a type, that's a type, that's a type. Be careful. This is not one atom. Make sure you separate them. This is a type, this is a type, right? Boom, boom, like that. And to find the number, obviously, it's going to be the subscript, right? So that's going to be 3. This 2 is signifying that this parentheses has 2. So you multiply this to each of the numbers to find out what they are, right? So let's look at this. Magnesium, there's going to be 3, right? For this one, you multiply this into this, right? So this is going to be 2. Oxygen is going to be 8, right? For this one, just 1 barium and 2 that. This one has just 1. And this one, again, you're multiplying this to both, right? So 2N and 4 O's. Right? Oops. And then Ca1O, remember 2, and H also 2. All right. So for 37, right? What we have to do is we have to write an electron configuration and a Lewis symbol for N, right? So let's look at the periodic table to see how to do that. Remember, to write the configuration first, you got to keep tracing it through until you reach where we're trying to get to. So these two, helium and hydrogen, are gonna add up to 1s, right? To 1s squared, right? And then tracing it too, this is gonna be 2s squared, and then this is gonna be 1, 2, 3, right? So 2p3, right? Because you're going, this is the s block, and this is also s, and then this is the p block, right? So this is going to be the electron configuration. Now we have to write a Lewis symbol. So basically for the Lewis symbol, all you're going to do is find the number of valence electrons, which is the ones in the highest shell number. So every single one with the number 2, right? So 2 plus 3 is 5. So there's going to be 5 valence, right? So what you're going to do is you're going to take the letter N, and you're going to draw 5 of these dots around it. So the correct order, I think, from the answer key to how to draw them, or 5, is going to be 1, 2, 3, 4, 5. This is going to be the correct thing. I don't think they're going to take points off as long as you have 5 of these around it. I don't know exactly what order to fill it up. I do believe it goes 1, 2, 3, 4, and then you start adding doubles onto each one. But for this, this is how it's going to look for 5 usually. Okay. All right. So for this one, you want to watch out because this has the word ions. All right. So what that means is you're not just writing Lewis symbols for the two atoms. You're also writing it for literally the ions. And that's the reason they're ions is because when two atoms bond in a molecule, they're gonna share electrons, and that's how they're gonna make sure they both reach octets. Now, an octet is basically if you want to count the number of valence electrons each of these have, this is 1, 2, 3, this whole row, right? 3, 4, 5, 6, 7, 8. 8 is where everything wants to be. So these all are like good. Like this is where every atom wants to be with 8 octets. Now I'm sorry, fluorine is 1 removed from that this way, and Na is 1 this way, right? So what that basically means is that this has an extra electron, and this is missing 1 electron. So it wants to transfer 1 electron from here to here, so that this can get pushed back 1 and this can get pushed forward 1, and they both reach octets. So basically, to simplify it a little and make so that you can understand it, right? Na, the loose structure is going to look like that. And F, it's going to have 7, right? So 1, 2, 3, 4, 5, 6, 7, right? Now, if you notice, right, this has 1 electron and it wants to transfer here because then this is going to have 0 around it and this is going to have 8, and those are both way more stable, right? So what happens when you lose an electron? The charge doesn't go down, it goes up. Why? Because electrons are negative charge, right? So when you lose the electron, when this electron comes over here, right, this is just going to be Na. And what happened? We lost an electron, right? So what happens to the charge? It's negative. It becomes more negative. Or sorry, it's positive. It becomes more positive, right? Because you lose an electron, you lose negative energy. And when you lose negative energy, you get more positive energy, right? Now, fluorine, it's going to have the opposite effect, right? Um, you add an electron, so you get more negative energy, right? So it's going to be, first of all, let's draw the 8 electrons around it. 5, 6, 7, 8. And draw this for, just clarity, making sure we know that this is what we're talking about is negative. Boom. And that's how you do it for the first question. Moving on to the next one. Again, we're going to be looking at these on the periodic table. Ca is over here. O is over here, right? O needs 2 electrons, and Ca wants to lose 2 electrons. So let's draw Ca with 2, and let's draw O with 6, right? So now we take these and we move them into this one, right? So then this becomes Ca and 2 minus. Now, I don't know why or sorry, 2 plus, right? Now, I don't know why we don't write plus 2. Like, really, it makes more sense to have the plus in front of the 2, but in chemistry, it's how you do it. Don't ask me, I didn't invent this. Chemists did. And then for the O again, oh, well, 1, 2, 3, 4, 5, 6, 7, 8. This is all good. This is going to be 2 minus, right? Now, for the next one, it gets a little bit more tricky. Why? Because we're not just dealing with 1 of each, we're actually dealing with 2 of each one this time. So, again, let's just jump right into it. And look at where these are on the periodic table. So SR is over here. It needs to lose 2, right? And which one's the other one? BR, right? That's actually over here. So it only needs to gain 1, right? So now you're probably thinking, okay, well, if it only needs to gain 1, the other one needs to lose 2. How's that going to work out, right? That's because there's 2 of these, right? So SR we know is going to lose 2. So let's skip this step that we've been doing. Let's just skip it, right? And jump straight into the ion. So SR, we know, is going to be 2 positive, right? Because it loses 2, right? And BR is going to be 1 negative, right? So that's good and all. And BR is going to complete the octet 1, 2, 3, 4, 5, 6, 7, 8, right? That's good and all. This doesn't line up though, right? Because there's a 2 here. So what we're going to do for this is, I'm going to put parentheses again, and we're going to put a 2 over here. to signify that there's one of these and two of these, and this one has a negative charge. And when you multiply this, it adds up to -2 charges, +2 charge, right? Boom, everything's balanced. We're all good. Everyone's happy. And for the last one, similar thing. Let's look it up where it is. All right. So for this one, similar thing except in reverse now. K is over here, it wants to lose one, right? And then O is over here, it wants to gain two, right? So K we can write, and remember this is 2K, so let's just skip there, right? 2K and then plus, right? And then O 2 minus, right? And then add the octet. Um, Hopefully this should make sense by now. And yeah, that's basically it. And literally once you understand how to do it, doing that's a piece of cake. I mean, that probably makes a lot of sense, hopefully. All right, so this is gonna take what we did in the last question and make it a bit more complicated, right? So let's look a little closer at this. SR and SE, right? Sorry if I'm not saying the right chemical names. I don't have them all memorized. I know I should, but I really don't. So, anyways, let's look here. So SR, right? It wants to lose two, right? And SE wants to gain two. So guess what? That works out perfectly, right? So if you want to form the compound, right? What we did in the last question was literally write out the things, right? Actually, let's do that again. Actually, I think we have to write them out. So SR wants to lose two, so it becomes 2 positive, right? SC wants to gain two, right? So it becomes 2 negative. And boom, everything works out. This would have the octet, right? And basically what this is showing is that we gotta have one of each for everything to be balanced. So the what's it called? The compound that would form would be SRSE, right? Now, looking at the next one, sorry, I'm just double checking my answers to make sure I'm giving you the right answers. All right, looking at the next one, oh, whoops, it gets a bit more complicated. Why? Because these are not the same. Or here, let me show you. So BA is over here. It wants to lose two, right? Now what's the other one? CL, right? CL actually only wants to gain one. So if we write that out, BA wants to lose two, and CL only wants to gain one, right? So to make this balance, what we actually need to do is we need to have two of the CLs. So we move this over and we add a 2 in front, right? Now what this is going to do is this is actually going to make this have more more electrons to give, because this actually has 7. Each of these only have 7, right? So, and this one has 2 extra electrons. This is not part of the Lewis structure. I'm just drawing this so you know, right? So if we have 2 CLs, then one goes to the first CL and then one goes to the second CL. And then everything gets balanced out. The CLs both have 8s and the BAs have 0. So it all works out. So if we draw this, what it's actually going to be is BaCl2, right? To make sure we have 2 of those, right? NAS, same thing, just in reverse, right? So if we look at this, NA wants to lose 1, S wants to gain 2. I'm not gonna waste time drawing this out by now. You should probably know you should already know how to do that by now, but you probably already know it's gonna be NAA2S, right? And then aluminum and oxygen. Aluminum has, let's see, 1, 2, 3 valence electrons, right? And then oxygen has let's see, 7, 6, right? Yeah, so 3 and 6, right? So let's draw those out. Now, aluminum, uh, it wants to, and here, you can ignore this part in the middle, um, because the only important part is that aluminum wants to lose 1, 2, to get to 0, right? Actually, no, it wants to lose 3 because that's 3 valence electrons, right? So it wants to lose 3. So we can do Al as 3 positive, right? And then oxygen wants to gain 2, right? So then O is 2 negative. Now, there's no clear, like, let's say we doubled the ALs. This would be 6, and that wouldn't be balanced. Let's say we doubled the oxygen. This would be 3, and this would be 4. That wouldn't be balanced either. So the only real way to make these two balanced is here's what we're going to do. We're going to double this and triple this. So AL2 and O3. So what this actually gonna do is this is gonna make this 6, and it's gonna make this 6, right? So now each of these are 6, everything's balanced, and we're all good to go. Um, we can fill in these two since we're here, right? Um, boom, boom, everything's balanced, and yeah. Okay, also one correction that I want to make on this is for each of these diagrams, this one's gonna have 8, this one's gonna have 8, this one's gonna have 8, and it's gonna have 0. So basically you're showing which ones are 0 and which ones are 8 for the Lewis symbols and for these. Alright, so for this one, we have to write a formula for the compound that forms between calcium and each of these polyatomic ions, right? So I'll just go ahead and start writing calcium for each of them. Now, you do have to have all the ions memorized, and all their charges too. So there's a table for that. There's Quizlets. You could probably find one, but I'm just gonna go ahead and assume that you do have them memorized. Um, so for the first one, it needs hydroxide, right? So that is OH, and then for the second one, it's chromate, which is CrO2. And for the next one is phosphate, which is PO4. And then for the next one, it's cyanide, which is C. So, hydroxide has a charge of -1. Right now, if we look to the periodic table, we can see that calcium has a charge of +2. Right. Um, so to balance these out, you're gonna need two calciums, right? So, sorry, to balance that, you need two hydroxides, right? So your equation is gonna end up being um calcium, and then put this in parentheses to make sure you're capturing the whole thing, and then 2. That's it, right? Now, CrO4 chromate has a charge of -2, which means that this is already balanced as is, which means that this becomes CaCr, just, I'm sorry, O4. Oh, well, this is actually chromate is actually, oh, whoops. There we go. And this becomes, oh, there we go. Yeah, I knew something was off. All right. And then phosphate has a charge of 3 negative, right? And C is 2 positive, right? The only way to make these equal is to multiply both of them by some value. So we're gonna multiply the calcium by 3, and then multiply the phosphate by 2, and that's gonna be that one. And then for the next one, cyanide has a charge of -1. So what we need to do to balance it out is just have two cyanide. So CA, CN, then parentheses, and 2. Alright, for this one's pretty straightforward. Since it's ionic compounds, you basically just gotta write what you see. And for the last one, use "-ide". Okay, for all of them, we're gonna use "-ide" to end it. What does that mean? Well, I'll show you. So magnesium nitride. There we go. "-ide", right? K is potassium, right? So this would be potassium fluoride. No, fluoride. Is that how you spell it? No, whoops. Okay. The fluoride. There we go. Sorry. This would be sodium oxide. This would be lithium sulfide. This would be cesium fluoride. And oh my gosh, wait, did I write it wrong again? Oh my gosh. Fluoride. There we go. There we go. That's how you actually write it. The last one is gonna be put oh, sorry. Potassium iodide. And yeah. Alright, so this one's pretty straightforward. It's the same thing we've been doing, kind of, but this time it uses polyatomic ions, so you gotta be careful, right? So for the first one, let's just start off copper. Now there's a list of metals that you have to specify the charge. Copper is one of them, and lead is one of them, and you just have to memorize. It's a list. So I'll just tell you which ones they are for now, but you can find the list table 4.3 in the textbook. Um, so let's do this. So we know that this polyatomic ion is nitrate. I'm pretty sure. Yeah. No, sorry, it's nitrite. So this is nitrite, and it has a charge of -1. So we know that to balance this out, the copper has to be +1, right? So then to mark that positive, we use the Roman numeral I, copper I, and then nitrite. And then for the next one, um, we're at a magnesium. And then this one isn't one of the ones we have to specify, but this is a negative, right? But we have this 2 over here, right? So this is going to be a -2. So then magnesium is right here, and it is a +2. So this is already balanced. So we can just write out magnesium acetate. And then this one is nitrate, right? This also has a charge of -1. Barium, right, is barium is over here on the bottom left. It's +2, right? And then nitrate is -1, but then there's a 2 here, right? So this multiplies, this becomes -2. Barium is +2, this is -2, so then it becomes, so they're already balanced, so you don't have to say anything other than just the names. Oh, whoa. And for the last one, it's lead. Lead is one of the ones you have to specify. So remember, this is -1, right? This is acetate -1 multiplied by this 2. So to balance it out, the lead has to also be 2, +2, so that when the acetate is -2, it balances out. And yeah, that's how you do that one. Alright, so this one's a little more straightforward. You just have to write out the formula for each ionic compound, which means take the first part and the second part. Right, so the first part of this is sodium, which is Na. The second part is hydrogen sulfide, right, which is HSO3, right? And sodium is a +1 charge, sulfide is so hydrogen sulfide is -1. They're balanced. That's all you need to do. Next one, lithium, Li, and then paramagnet, right, which is Mn O4. And then again, lithium has a +1. The paramagnet has a -1, so they balance out. That's all you need to do for that one. Now silver nitrate, right? Silver Ag, and nitrate is NO3. This has a -1 charge. This has a positive charge. Although this one, for the charge of silver, this one's actually harder to tell from the periodic table, because all of these you can look and they're like in group 1 or group 2 or something, right? Silver isn't really, it's kind of in the middle, which is harder, but just remember that silver has a +1. It might not be on a test, a question like that. um and then sorry, potassium sulfate, right? Potassium is K, and then sulfate is SO4. Now I'm gonna take a little closer look at this, all right? So first of all, we know SO4 is a 2 negative, right? And potassium, if we look it up in the periodic table, it's only a +1, right? So that means this is uh +1, and this is a 2 negative, which means to balance this out, we actually need 2 potassium, so it's K2SO4. Um, then for the next one, rubidium, Rb, and then another hydrogen sulfate. Um, this one also doesn't really have any balancing issues because it's a +1 and a -1. And then the next one's potassium, and then hydrogen carbonate, which is HCO3. And again, potassium is +1, this is -1, cancel out, everything works out. All right, these ones are pretty straightforward. For these ones, all you gotta do is, since they're molecular compounds, right, all you gotta do is if the first one is more than 1, then you add a prefix, and the second one you always add a prefix. So really straightforward, right? First one, it's just 1, right? So you do carbon. And the second one is 1, right? So you got the prefix monoxide, right? Now the next one. The first one is just 1, so nitrogen. And then the second one is more than 1, right? It's 3, so triiodide. And then the next one is just 1, silicon, and then it's 4, right? So tetrachloride. And then the next one is 4, so you gotta put a tetra. Gotta put tetranitrogen. And then tetraselenide. Boom. That's it. Pretty straightforward. This one's also pretty straightforward. Same thing in reverse is the last question. This one doesn't have a prefix, so this is just one, right? So phosphorus is P, and then trichloride, right? So Cl3, right? Next one is chlorine, which is Cl, and then one oxygen, right? So ClO. Next one is disulfur, so two sulfurs, and then four, this is tetra, four fluorides. And the next one is phosphorus and five fluorides, and that's it. All right, this one seems a little harder, but it's really not. All you gotta do is just combine what we've been doing. So first of all, we gotta figure out whether these are ionic or molecular, um, because that has different rules for each, right? So this one, first of all, we know that this is a polyatomic ion, right? So, and this is potassium, so this one's gonna be ionic, right? Since it's a polyatomic ion, it's gonna be ionic, right? This one is gonna be, um, sorry, this one is a metal and this is a non-metal, so we know this one is going to be molecular. And this one, actually, let me just write them down. Ionic, molecular, and this one is also going to be ionic just because again, it's another polyatomic ion, right? So then to write the name of this is just potassium, and then the polyatomic ion, which is chlorate. Uh, Pretty straightforward. This one is di. Remember, so the first one is 2, so it's diiodide. Um, Sorry, it's not diiodide. It's just diiodine, and then pentoxide. Um, And then the next one is ionics. We gotta follow those rules, right? It starts off with lead. Remember, lead is one of the ones where it can have multiples. We gotta put the parentheses. SO4 is sulfate, right? Um, and we know that sulfate has a -2 charge. So lead has gotta be +2 to match that. And boom, that's it. Alright, so formula mass. What is formula mass? It's pretty simple. You just take this, multiply it by the atomic mass, and then take this multiplied by its atomic mass, and then just add them, right? So let's just do it really straightforward, right? So one atom of N, right? So what's the atomic mass of that? So it's just one, right? Times what's the atomic mass? Let's look at the periodic table. The atomic mass of N is 14.01. 14.01, right? And then we add on 2 times the atomic mass of oxygen. What is the mass of oxygen? 16. So 2 times 16, right? And this is equal to 46.01 AMU. And that's our answer. Now for this one, same thing. 4 atoms of carbon times what's the atomic mass of carbon? 12.01. And then we add on 10 hydrogen times what's his atomic mass? It is 1.01. Then we just do the math. And it is 58.41 AMU. And oh, sorry, 58.14 AMU. Right? So we're just taking each atom, how many times it is, right? And we're multiplying that by the atomic mass. You could do the same thing for these two. I'm not gonna write them out for interest of time, but I will I will just tell you the answers. 80.18 AMU, and this one is 238 .02 AMU. And those are the answers for those two. All right. So for this one, we need to calculate the number of moles in each sample, right? So they give us the grams, and we define how many moles there are, right? Now, pretty straightforward. the first step is just doing what we did last time, is calculating the molar mass, right? So for the first one, there's 1, and then the mass of that is 12.01, right? So times 12.01, right? And then let's add on the other one, chlorine. There's what, 4 of them? Yeah, 4 chlorines. And the mass of chlorine is 35.45, right? Now do this and we get what? 153.48, I believe. No, sorry, 58. What is this? This is grams per mole, right? So for every mole, there's this many grams, right? Now, this is what we have. We have, so yeah, sorry, for every mole, there's this many grams, right? Now, instead of giving us the moles, it's giving us the grams, right? So we have to flip it. So let's take what it's giving us. So 72.5 grams, right? Multiplied. Remember, the grams needs to be on the bottom. So let's flip this upside down. So let's do 1 mole on the top and let's take this and put it on the bottom, which is 153.58 um, grams, right? So then grams cancels out, and when we do the math, we're left with 0.471 moles of CCl4. Boom, pretty straightforward. I'll just do this one more time. And then you should know how to do it for the other two. Um, so let's do this one, right? There's 12 of these. So do 12 times carbon's mass, which is 12.01, right? Then there's 22 of the next one, right? Times the mass of hydrogen, which is 1.01, right? And then there's 11 of the next one times oxygen's mass, which is 16. Right? And we take that and we get 342.32 grams per mole. And then we take that, right? And then we take this and we multiply it, right? 12.4 grams times 1 over 342.32. And this is mole, and this is grams, right? Cancel, cancel. What do we get? We get 0.0362 moles of C12H22O11, right? And that's our answer. Now for this one, again, you basically do the same thing that we've been doing. Um, except remember this one has a kilogram, so make sure you watch out for that. And for the dinitrogen monoxide, it's a molecular compound, right? So all you gotta do is, before doing this one, turn this into a molecule. This is dinitrogen, and then monoxide, this is N2O, right? So yeah, do that and then solve this, and you should get your answers for these two. I can write them out so that you can check, but this one would be 968 moles, and this one would be 0.279 moles. And yeah, that's how you do these ones. All right, so for this one, I don't really want to cover it too much because, well, the last question was basically the same thing. All you're doing is taking the number of moles and then multiplying it by Avogadro's number. I think that's his name. I don't know. Um, and which is, what is it? 6.02 times 10 to the 23, right? And then that's your final answer. So I don't feel like I need to do all of these. If you watch the last question, just multiply those answers by this, and you know, that's your final answer. All right, for these ones, I'm gonna go kind of fast. It's well, it's kind of similar to what we've been doing, right? So first of all, now we're doing what we just did, but in the reverse. So we gotta first of all find the molar mass of SO3, right? So let's just do what we're doing, right? 1 times what's the mass? It's 32.07, right? And then plus what? Plus 3 oxygen molecules, right? Oxygen atoms, and each of those have a mass of 16 grams, right? So the molar mass is going to be 80.07 grams per mole, right? Now, instead of multiplying it by the grams, we know that we have this many moles of molecules, right? So we can directly multiply, well, here's the thing. We don't have this many moles, we just have this many molecules, right? So, let's write it out. So we have 5.94 times 10 to the 20 molecules, right? Now, we need to figure out how many moles this is, right? So to do that, we can multiply by Avogadro's number, right? So that's gonna be, what is, well, sorry, we don't multiply, actually, no, yeah. We, sorry, we divide by Avogadro's number, because 1 mole is equal to 6.02 times 10 to the 23 molecules, right? And this is also molecules. So then these units cancel out, right? So then this is equal, um well, we multiply by Avogadro's number, right? And now we have the quantity in moles, right? Now, once we have the quantity in moles, we can use this conversion factor, right, of 80.07 grams per mole, right? And we can cancel out the moles, and then we do all the math, blah, 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 yada, yada, yada. It gets us 0.0790 grams of SO3. And then I'll do one more just so you know how to do it, and then you can do the third one on your own. Um, so we have 2.8 times 10 to the 22 water molecules, right? We multiply this by Avogadro's number, or divided by Avogadro's number, so that we can get it in the number of moles that we need, right? And then we multiply this by the molar mass of water, which is, well, it's, sorry, it's 2 hydrogens times 1.01, right? And then plus um 1 oxygen times 16, right? And then over 1, right? We do all the math, yada yada yada. It's 0.84 grams of H2O. Right. Now for this one, you can do it on your own. I'll just tell you the answer so you have it. It is 2.9930 times 10 to the negative 22 grams of C6H12O6. Again, pretty straightforward question, right? Same thing as we did in the last question, right? Um, we have this many, what's it called, molecules, right? So what's its mass? So we start off with molecules. Um, Now let's convert the molecules to moles using Avogadro's number, right? 1 mole over 6.02 times 10 to the 23, right? Molecules, right? And then now we have to multiply this. Now we have the value in moles. Now we got to um convert it into grams, right? So we got to use the molar mass of this, right? So we have 12 carbon atoms, right? So 12 carbon atoms times 12.01 atomic mass, right? And then we have 22 hydrogen atoms times the atomic mass of that is 1.01. And then we have 11 oxygen atoms times 16, right? 16 grams. And then we have all of that, which is the same as 1 mole of this molecule, right? Cancel units, boom, boom. Um, final answer is we get, well, okay, here's the thing. We can't jump to the final answer yet. You know why? Because there's one thing we're missing, and do not miss this. Okay, be really careful. This is not asking for grams, it's asking for milligrams, right? So we have to add one more thing into our conversion or into our big equation, which is that well, we have grams over here. Right? Let me just write this in grams, right? So we need to have a way to cancel out the grams and make it milligrams. So we know that for 1,000 milligrams, there's 1 gram, right? The 1,000 has to be in the top because then because then then the grams and the grams can cancel out, right? So then this is gonna be on the top over 1 gram, and your big answer is gonna be 0.10 milligrams of C12H22O11. Boom. All right, so for this one, you need a conceptual understanding of what's going on to answer this question, right? So let's see. So it's saying that a lot of fertilizers have nitrogen containing compounds such as this, and this, right? So ignore this, blah, blah, blah. Oh my gosh. We don't need this sentence right here. Ignore that. Okay. Calculate the mass percent composition of nitrogen in each of the fertilizers, right? And which one has the highest. Okay, so basically what it's asking us to do is find out the amount of nitrogen in each of these, like the percentage of nitrogen in each of these. And really, how to figure that out, how to figure out the percentage at all of nitrogen in, or the mass percent, right, is to figure out how much nitrogen is in the total, right? So nitrogen, or well, nitrogen over total. And it's not just how much nitrogen atoms, it's nitrogen mass over total mass, right? Because if we were just doing how much nitrogen is in this atom, it's 1 nitrogen to 3 hydrogen, right? So it's 1/4, right? But that is, so 1/4 is not the right answer. We need to find the mass first before doing any of that, or before getting the right mass percentage, right? So first we got to find out just the mass of nitrogen on its own, right? So nitrogen is, well, just 1 nitrogen atom, right? Times what is it? 14, oh, sorry. Um, 1 nitrogen times 14.01, which is the atomic mass, is just 14.01 grams per mole, right? So for every mole, nitrogen is 14.01 grams, right? And then let's find the total in this one, NH3, right? So we know that there's 1 times 14.01 nitrogen atoms, right? Plus 3 hydrogen atoms, and each of those are going to have 1.01 as their mass, right? So that's going to give us 17.04 grams per mole, right? Now what did we say? We need to divide the nitrogen over the total, right? So let's do that. 14.01 over 17.04. What does that give us? That gives us 0.8222 or 82.22%, right? This, well, 82.22% nitrogen, right? So this right here is the mass percent composition of nitrogen in this one, right? Now we got to repeat that for this and this and this, right? So I'll just do another one, and then the other two you can do on your own. But for this one, right? Let's do this one. Okay, so in this one, it's a little bit more complicated because in this first one there was only 1 nitrogen, right? But in this one, there's not just 1 nitrogen. There's one, but that's multiplied by 2, so there's actually 2 nitrogens in this one, right? So we gotta account for that. So let's find the amount of nitrogen. So it's 2 times, let's find the mass of nitrogen, right? So it's 2 nitrogens times 14.01, which is equal to 28 0.02 grams per mole, right? And then the total is going to be one carbon atom, which is 12.01, right? Now, one oxygen atom, which is 16 grams, and then um, two nitrogen atoms, right? 2.1401, right? Plus four hydrogen atoms, right? Because it's this two times this two, right? So four hydrogen atoms, each of those are 1.01, right? This is equal to 60.07 grams per mole, right? Then what we have to do is we have to divide this by this, right? So this becomes 28.029. Oh, that's not it. That's a G, sorry. 20.02 over 60.07, which is equal to 46.65%, right? So we can already see that this one is going to be higher than this one. So we already know that this one is not the right answer, right? Now, I'm not going to do the other ones because, well, it's the same process again, over and over again, right? But I can just tell you the right answer is going to be this because it has the highest, because um the other ones like 35 something, this is like 21% something, right? And then this one was 60% something, right? And this one is like 80. So this one is going to have the highest mass percent composition of nitrogen. And yeah. All right. So this one is a little more conceptual than it is practical. But once you get it, you get it. So let me just try to explain the best I can, right? So what it's saying is this element contains this much fluorine by mass, right? So what's that saying is like if this is copper to fluoride, right? Then 37% of that would be F, and then the rest would be copper, or copper, and then the rest of the other atoms that make up fluoride, right? But, or actually, no, sorry, the rest would be copper, right? And 37.42% of it is fluoride, right? So then it's saying we have 55 grams, right? So the total is 55 grams. And if 37% of that is fluorine, then how much fluorine is there, right? So once you see it like that, it's pretty straightforward, right? You're taking the total, right, which is 55.5 grams, and you're just multiplying it by this percentage times, well, here's the thing with percentages, right? You move the decimal spot 2 points back, so it becomes 0.3742, right? Make sure you don't multiply it by this, right? Make sure you move the decimal 2 spots back because it's a percentage, right? And you take the total, you multiply it by the percentage, right? And then you should just get your answer of how much fluorine is in it, right? 20.8 fluorine in grams, or well, grams of fluorine, right? Pretty straightforward. Once you understand how to do it, it's not that hard. It's a little tricky wording though, if you don't fully know what mass percent composition is. All right, this one is just pretty straightforward. Ignore all of these. We're just gonna take a look at one of these, okay? Because these are all the exact same thing, right? So we just need to look at one of these, and remember, the red is oxygen. The black is carbon. Um, and the white is hydrogen, right? Now, what we're gonna do is we're just gonna look at the numbers, right? So this is literally it's this easy. It's two hydrogen to one oxygen, because literally for each one there's two hydrogen and one oxygen, right? This one you could tell, right? Four hydrogen to one carbon. And this one is six hydrogen to two carbon to one oxygen. Now, I know this is a little confusing because the carbon's kind of hard to see, um, but that's really the answer, and it shouldn't be too hard once you know how to do it. This one, again, easy problem. So we have this many moles of this, right? So that means we have this many moles of 4C, and we have this many moles of 10 hydrogen, right? So what are we trying to find? We're trying to find the hydrogen in each of these, right? So we have this for 10 hydrogen, right? So to find it, we just multiply it, right? Because this total molecule is multiplied by 0.0885, right? So that means this is multiplied by that and this is multiplied by that. So let's just do that. So 10 hydrogen atoms, right? Multiplied by the moles, which is 0.0885. And what does that give us? 0.885 moles, right? Um, Now let's do this one, right? So there's 4, right? So 4 times 1.3, right, is equal to 5.2 moles of H, right? Sorry. And there's 12 of these times 2.4 is equal to 29 moles of H, and this one has 18 times 1.87, right, which is equal to 33.7 moles of hydrogen. And yeah, just straightforward. All right, so for this one, I have my own method. It's a little different than the one in the answer key, but it gets the same answer, and I feel like it makes more sense. So I'm gonna explain it that way. So first of all, you have 8.5 grams of this, right? And or this, or this, or this, yada yada yada. And now out of those 8.5 grams, you want to find out what percentage of it is Na and what percent of it is everything else, right? So let's start. So what I do first is I find the mass percentage of like Na in this whole thing, right? So what is Na out of the whole thing, right? So the mass of Na over the mass of NaCl, right? And for that I'm gonna, well, the mass of Na is just going to be one atom of Na, right? Times, let's see, times 22.99, right? And then the mass of NaCl is going to be, well, 1 times 22.99, right? Plus 1 chloride atom, times, what's chlorine? Chlorine is over here at 35.45, right? And it's going to give us that percentage, right? And now we're going to take this percentage and we're going to multiply this by 8.5 grams of table salt, right? And the answer that this gets us is 3 point, well, it's about 3.3 grams of sodium in this, right? So that's our answer. And now moving on to the next one. Now for this one, we're just gonna repeat that, right? What's the mass of Na? It's 3, right? 3, because it's 3 sodium atoms, right? 3 times 22.99 all over. What's the mass of the entire thing, right? 3 times 22.99 plus phosphorus, one phosphorus atom, right? Which is um or yeah, sorry, my brain. 30.97 plus 4 oxygen atoms, right, which is 4 times 16. Well, that's also multiplication. Okay, good enough. And then now this right here is the percentage, how much sodium is in the entire thing. Now we multiply that percentage by the 8.5 grams, and we should get around 3.6 grams of sodium. And yeah, you're gonna just repeat that method for this one and this one. You should get, well, you should get specifically these answers, which is 1.4 grams and 1.7 grams of sodium. And yeah, just follow this method, you'll be all fine. All right, now for this one, it's tempting. It really is tempting to just use the grams as they are, right, to calculate the empirical formula. But you can't do that. Okay, you gotta convert grams to moles always before doing stuff like this with like empirical formula, number of molecules and stuff. Now, now let's rewind a bit. What is empirical formula? That's like that's all we're looking for is the formula of, well, first of all, we're just making a formula like this, like Ag with some subscript and then O with some subscript, right? And then the empirical formula is we're taking that and we're just making it as like we're simplifying it as much as possible. Like if it was like Ag4 and O2, the empirical formula would be Ag2 and then O and then just 1, right? So anyways, that's basically what we're looking for. Now to figure out what that is, right, we got to figure out how many of each atom are in the molecule, right? So this is in grams, but this isn't how many atoms, this is the weight, right? This is the mass, sorry, not the weight. This is the mass. We got to convert the mass into moles. So let's do that. So let's take the 1.651 grams, right, of sorry. Let's take the 1.65 grams of Ag and multiply it by the molar mass, right? So if we go here, um well, not by the molar mass. So where is it? Right here. So 107.87, right? So if we take this, so this is 107.87 grams per mole, right? Now we're trying to cancel out the grams, right? So we have to put this on the bottom, right? To cancel this out. So that means we have to flip this fraction over. No, we have to flip it over and turn it into a fraction. So 1 mole is over 107.87 grams, right? And this is gonna give us how many moles of Ag we have. So sorry, I lost the tab. So that is gonna be 0.0153 moles of Ag. Now, we're gonna do the same thing for oxygen. Now I'm gonna fast forward a bit since you know how to do it now. And it's gonna be 1.224 grams times 1 mole over 16 grams, right, for oxygen. Cancel, cancel. This becomes 0.00 765 moles oxygen. Okay, so now we have to take these two numbers and we have to find out what's the ratio between them, right? Because that's going to be able to give us our empirical formula, right? And the easiest way to find that ratio is just to divide them by each other. So this is a bit the 0.0153 is the bigger one. So let's divide 0.0153 over this 0.00765, and that's equal to 2, right? And then now we know that the ratio is 2, right? So there's got to be to make this equal, there's got to be 2 oxygen atoms for every one. um I think Ag is let me look it up. Yeah, Ag is silver, right? I don't know how I forgot that. Um, sorry. Ag is silver, right? So there's gonna be 2 oxygen atoms for every 1 silver atom there is, right? So if we were gonna write out this empirical formula, the answer would be um Ag2O, right? And there we go. That's our empirical formula. Um, and now moving on to the next one, right? We're gonna do the same thing, and we are gonna take and here, let me write this down here so it's a little bit neater. 0.672 grams of I think this would be cobalt, right? Or, oh, give me a second. Yeah, sorry. I don't know why that took so long. This should be cobalt, right? So, if we look that up on the periodic table, that is gonna be right here, 58.93, right? So 1 mole over 58.93 grams, right? Which is gonna give us a mass of 0.0114 moles. Or sorry, not a mass. It's gonna give us a number of 0.0014 moles, right? And then 0. Moles of cobalt, right? And then 569 grams times 1 mole over for AS, it's 74.92, right? And this is gonna give us 0.0076 gram, sorry, 6 moles of AS. And this one is gonna be 0.486 grams of oxygen, right? So it's gonna be 1 over 16, um, which is gonna be um 0.0304, right, moles of oxygen. Now, here's the thing. For this one, it's going to be a little bit more complicated since we're not just dividing two, right? One, two, three different numbers we got to keep track of. But still, it's doable. So let's do it, right? Um, so the trick is to divide all of them by whatever one's the smallest. So here we see the smallest is the 0.0076, right? Um, so we're gonna divide 0.0114 by that, and we're gonna first of all, that is equal to 1.5, and then we're gonna divide 0.486 by that, um, which is gonna be 4. And we are going to divide itself by that. And you don't really have to do this. This is just kind of something to do that kind of helps you keep track of what's going on. It's going to be 1, right? So what is this saying? This is saying that for every 1 AS, right, there's going to be 1.5 cobalt and 4 oxygen, right? Now, how can you have 1.5 of an atom? That doesn't make sense, right? So obviously, to make this make sense, we're going to have to multiply all of these by 2, right? So, um, for the answer, well, let's just write out the symbols, right? And let's ignore this for now. So, COAS and O, right? Now for cobalt, this is gonna be 1.5, right? For AS, it's gonna be 1, and for 0, it's gonna be 4. I'm sorry, for O, it's gonna be 4, right? But what did we determine? We have to multiply all these by 2, right? So this is actually gonna be 3, it's gonna be 2, it's gonna be 8. And that is your empirical formula. Now, here's the thing, is technically there's a polyatomic ion that's ASO4. So the real correct way to write this part would be to scratch this and write ASO4 and then put parentheses around this and write it 2. But the thing is, we're only in Chem 130, we don't have to memorize that, so this is still the right answer for our purposes, even though in reality it's not. But yep. Then for C, you're gonna do the exact same thing. I mean, I don't think I have to explain it. You can just follow the steps we used for the other ones, and yeah. All right, guys. Now this one, we're gonna do another empirical formula. Now, here's the thing. This is the mass percent composition. Okay, these numbers they look nice, but they're mass. Okay, do not use these numbers, okay? I mean, use the numbers, but you got to convert them into moles, okay? Please, 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 when you see the word mass, be careful and convert it into moles. Well, I mean, depending on the question. But for this one, you do need to convert into moles. If you don't, you'll get it wrong. And just be careful. So let's do this, right? So, let's just say, so these are all percents, right? But we can just assume we have 100 grams of each, right? That way we can just use the numbers as is, right? So in reality, what I'm doing is I'm taking this and I'm making it a percent, right? 0.7569, and then I'm multiplying it by 100 grams, which just gives us 75.69 grams, right? So that's basically the exact same number. Yeah. So let's just multiply these by 100 grams to make life easier, right? So we have 75.69 grams of carbon, right? And now we need to multiply that by the molar mass, right? Carbons is 12.01 grams per mole, right? You gotta flip that over. 1 mole and then 12.01 grams. Cancel, cancel. This gets us 6.302 moles of carbon, right? And then for the next one, we're gonna multiply by 100 again, use 8.8 grams, right? Times 1 mole for hydrogen, it's 1.01 grams, right? So this is equal to 8.731 moles of hydrogen, right? And for oxygen, it's going to be 15.51 grams, right? Times 1 mole over 16 grams, right? Which is going to be 0.9696 94 moles of oxygen, right? Now we have all the moles, so remember the next step is to divide them by the smallest one here. The smallest one is going to be oxygen, so we're going to do 6.302 over 0.9694, right? And do 8.731 over 0.9694, and then just as a formality, we're gonna do this, itself over itself, right? um and this is equal to 6.5. This one is gonna be 9, and this one's obviously gonna be 1, right? And now we want to make this empirical, so this is a 0.5. The easiest way to get rid of that is multiply each of these by 2, right? So um and this is carbon, this is hydrogen, and this is oxygen, right? So if we were writing it out, we'd write CHO. We multiply each of these by 2 as we bring them down. So let's multiply this by 2 would be 13, this one would be 18, this one would be 2. And there is your empirical formula. All right. For this one, in the interest of time, and since I don't want to keep repeating stuff I've been saying in the previous questions, I'm just going to give you a more of how to do this than actually fully solving it, right? But basically, what you want to look at is you're combining this much nitrogen with this much chloride, right? So pretty straightforward, right? You're going to take 0. Well, first of all, you want to find the percentages of each of these, and then that'll let you, well, actually, now that I think about it, you don't even need to find percentages of these. You just want to find them how many moles of each, right? Is going to happen. So you take 0.77 of the milligrams, right? Um, you, I mean, yeah, you could convert it into grams, but you don't really have to since, well, I guess I'll do it just to be formal. So 1 gram, 1,000 milligrams, right? I'll just get that out of the way. Might as well. Don't really have to since empirical formula, it's all ratios anyways, right? But let's just do it as a formality. Um, this milligrams, right? 1 gram. And then what we're going to do is we're going to multiply it by the molar mass, which is 1 mole over again, to cancel it out, we got to put the grams at the bottom, right? So 14.01 for nitrogen, right? And then cancel, 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 right? And then for this one, we're going to do the same thing, 6.61 milligrams, multiplied into grams, and then multiply it again, 1 mole over what is it for chlorine is 35.45 grams, right? And then we're gonna get some number here, um, and we're gonna get some number here, we're gonna get some number here, we're gonna see which one is smaller, and we're gonna we're gonna take the smaller one and divide it by the larger one, right? And that's going to give us our ratio. And if our ratio is a positive number, good. Otherwise, if it's not, multiply it by like 2 or 3 or whatever until it is. And I'll just tell you that this one is going to be this times 3. The ratio is going to be times 3. So the final answer is going to be NCl3. This was actually pretty straightforward. So we're given the empirical formula and we have to find the actual formula, right? So we have to take this and turn it into like an actual formula. And how are we going to do that? Well, remember, empirical formula is more just ratios, right? We can multiply this entire thing by 2 and this becomes 12, this becomes 14, and this will become 2, right? So basically, this for whatever the real formula is, this is what the molar mass is. So we can find whatever our molar mass is here, right? And then we can take the official one and we can divide it by ours and see what the ratio is, right? And we take that ratio and we multiply this by that ratio. So here, let me actually do it and then maybe it'll make a bit more sense. So let's find the molar mass of this. So first thing we're gonna do, we're gonna take the carbon, we're gonna multiply it by the molar mass of carbon, right, which is 12.01, right? We're gonna add on 7 of the hydrogen. We're gonna multiply that by the 1.01 grams, or just 1.01, I guess, since I'm not using units. Which I probably should use units, but it's fine. It's fine. And then 1 mole of nitrogen, or 1 nitrogen, right, times whatever the mass is for nitrogen was 14.01. Yeah. So we take all of this, what do we get? 93.14, right? So this is 93.14, right? Now we want it to be this, right? Now if you look closely, oh actually not look closely, I don't think you could look at this. If you do the math, what you'll find is this 2. This is literally this times 2. So what does this say? That means that we have to take this and multiply it by 2, right? So that all we have to do is take this and multiply this by 2, and that. So our real formula or our molecular formula is going to be C12, H14, and N2. And yep, that's the answer to this one. And then for the rest of them, I mean, it's pretty much the same thing over and over. I probably don't have to repeat the explanation. It's literally the exact same thing. So just different numbers. So, do it yourself, try to work it out. I can give you what the actual answers are for these. This one is gonna be C6, H3Cl3, and this one is gonna be C10, H20, N2, and S4. And yeah, there you go. All right, now for this one, before we do anything, sorry, before we do anything, let's just get one thing straight, all right? This is a hydrocarbon, okay? Which means that the empirical formula, we have to calculate the empirical formula um for the hydrocarbon so the hydrocarbon did a reaction, blah, blah, blah. It formed this and this. Now we know law of conservation of mass. That means whatever the hydrogen and carbon was in this, it all went into this and this, right? So a hydrocarbon is only H and C. There is no O in a hydrocarbon. It's hydrogen and carbon. So for this, what we're essentially going to do is we're just going to ignore the O's, right? This literally doesn't matter. Mostly what we're looking for is how much carbon did we end up with and how much hydrogen we end up with. And that'll let us figure out how much how much of each was in the original, right? So let's do this. So first of all, before we do anything, let's just try to find how many moles of each, what's it called? How many moles of each molecule were produced, right? Because remember, we're in mass right now. To do anything with the empirical formula and the ratios, we need to be in moles, right? So let's take the 33.01 grams of CO2, right? And let's multiply it by 1 mole, right? And over the molar mass of CO2, right? So what is that? So that's one carbon atom times its mass of let's see, 12.01, right? Plus um two oxygen atoms, which are both 16, right? Um and basically what this is going to give us, sorry. So now we have how many moles of CO2 there were, right? Now for each mole of CO2, there's going to be one C and two O's, right? There's going to be one C and two O's, right? So we're only looking for one C, and guess what? We just found how many moles there were, right? There's only going to be one C for each of these moles, right? So we don't have to multiply by anything. That is just how many moles of carbon there were, um, which is 0.750, right? Now, sorry. Uh, okay. Now we're gonna do the same thing, 13.51 for the H2O, kind of. So we're gonna take this, we're gonna multiply 1 mole over H2O, which is two H's, right? So 2 times 1.01, um, and then plus 1O, which is 1 times 16, right? Now we have how many moles of H2O, right? Here's the thing though, for each mole of H2O, well, for each mole of H2O, there's two H's and one O, right? So, to find out how many, how many H's were produced, we're going to multiply this by 2 to get the actual number of H's, right? So this is the moles of the entire molecule, right? Now we're going to multiply that by 2 because inside of each molecule, there was two hydrogens, right? So 2. And what this is going to get us is 1.5 moles of hydrogen. So basically, all we did is we took the initial mass and we figured out exactly how many molecules were formed based on this mass, right? And um now that we have the number of molecules, right? Um in moles, we can take each of these molecules and we know that for each CO2 molecule there's one carbon atom, and for each H2O molecule there's two hydrogen atoms, right? Um, and then that gives us 0.75 moles of C and 1.5 moles of H. Remember, for the empirical formula, we divided by the least amount, right? So 1.5 divided by 0.75, right? What is that going to give us? 2. So the ratio is 2, right? So the formula for the hydrocarbon is for every one hydrogen, there are for every one carbon, there are two H's. And there is our critical formula. All right, so this one's the same thing. Well, not the same thing. It's similar to the last problem. You just add another step on. Um, so this time, the reason for that is because it's the original thing is butyric, whatever, butyric acid, right? And it's a compound containing carbon, hydrogen, and oxygen. Uh-oh, so now there's oxygen in the original one, so we have to do a bit more. That's fine. Let's break it down step by step. First of all, let's figure out exactly how many moles of C atoms and exactly how many moles of H atoms there are, right? So, again, so we know that, let's convert the grams into moles, right? So for CO2, well, 8.59, right, grams times 1 mole for every, well, 1 times C, which is 12.01, right? Plus 2 oxygen atoms, right? Um, so now we have the number of molecules, right? And we take the number, now for each molecule there's 1 carbon atom, so we just multiply that by 1, which doesn't really do anything, but it's a formality, right? Um, and if we take that, that is gonna be 0.195 moles of carbon, right? I don't know why I wrote out the whole thing. I probably shouldn't have. All right, then we're gonna take 3.52 grams of H2O, right? And we're gonna again divide it by its molar mass, right? So that's gonna be there's gonna be 2 hydrogen atoms, and there's gonna be 1 oxygen atom. 1 times 16, right? Yeah. And then we're going to multiply this. Remember, for each of these molecules, there's 2 hydrogen, right? So we're going to multiply 2, right? And that is going to give us 0.391 moles, okay, of hydrogen, right? Now, here's the thing, is we want to find out how much oxygen was in the original sample, right? I think because of the way combustion works, like conservation of mass is a thing. So you started with some C, some H, some O, right? You do your thing, and then oh, that's supposed to be an arrow. Sorry. You do your thing, you end up with some C, some H, some O, right? But there's also O in the atmosphere that can enter, right? So this is actually more O than you started out with sometimes. So what we actually want to figure out is how much O did we start out with, right? So to do that, here's the thing, the carbon and the hydrogen, they didn't change. Okay, these are going to be the same in the beginning and the end because of conservation of mass, right? So let's first figure out how much carbon and hydrogen were in the original sample. Or sorry, let's figure out how much carbon and hydrogen were in the original sample. So here's the thing, we have an original sample of 4.3 grams, right? And these right now are in moles. So let's convert these into grams, right? So we take this many moles, right? And we multiply it by the molar mass of carbon, right? What's the molar mass of carbon? So we're gonna do 1 mole on the bottom, because we have to cancel them out. And we're gonna do the molar mass, which is 12.01 grams on the top. Cancel, cancel, right? Um, and this is going to give us 2.344 grams of carbon, right? Now, same thing here. We're going to multiply this, right? We're going to put 1 mole on the bottom. Molar mass of hydrogen is 1.01, right? And then we're going to multiply it. It's going to be 0.395 grams of hydrogen, right? Now, this is how many grams of carbon, and this is how many grams of hydrogen we started out with, right? And this is how many were total. So if we take the total and we subtract carbon and we subtract hydrogen, we'll be left with how much oxygen we started out with, right? Perfect. That's exactly what we need. So let's take the total of the original, right? Let's subtract how much carbon we started out with, and let's subtract how much hydrogen we started out with. And what this is going to give us is 1.561 grams. This right here is how many grams of oxygen we started out with. Okay, cool. Now let's take this, G of oxygen, right? And let's turn this into moles, right? Because we have the moles of carbon, we have the moles of hydrogen, let's get the moles of oxygen. All right, so we want moles on the top, right? 1 mole. And what's the molar mass of oxygen? 16. You should know that by now. 16 grams per mole. So cancel, 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 cancel. And this is going to be 0.0976 moles of oxygen. Cool. So now we have how many moles of carbon, we have how many moles of hydrogen, now we have how many moles of oxygen, right? Now what do we do again with these 3 values? We divide it by the lowest one. What's the lowest one? This, right? So For carbon, it's going to be 0.195 over 0.0976. For hydrogen, it's going to be 0.391 over 0.0976. And for oxygen, it's going to be, well, 0.0976 over 0.0976, which is what, just 1, right? And this one, okay, let's calculate these. So carbons is going to be 2, and hydrogens is going to be 4, right? So 2, 4, 1. Look, these are all whole numbers. You know what? That's perfect. So now we don't have to do any math or thinking. We can just write these down as is. C2H4 and O1. And that is our empirical formula. Again, for this one, I'm going to use my own strategy, which is a little simpler, I think, than the one that they used in the answer key. But it uses the same numbers and it gets you the exact same answer. So here's how I would explain it. So we know that this releases 25 grams of this molecule, right? So to find out exactly what mass of chlorine, right, out of this, first of all, let's find how much chlorine is out of the total molecule, right? So let's do the mass of the chlorine over the mass total. And that'll give us a nice percentage, right? So what's the mass of chlorine? So there's 2 chlorine atoms, right? So 2 times, let's see. Chlorine is, oh, well, I have a lot of marks on here already. All right. Chlorine is right over here, 35.45, right? So 35.45, right? Um, and that's the mass of chlorine, right? Now let's put this over the mass of this total. So 1 times carbon, which is 12.01, right? Plus 2 times fluorine, which is 19, and then 2 times what we just had, right? The Cl, right? So there we go. Now, what we're gonna do with this number right here is this is the percentage of chlorine in the entire molecule, right? Now we're gonna take that percentage and we're gonna say, okay, well, what is that percentage of the 25 grams, right? So we're gonna multiply by the 25 grams, right? And but here's the thing. We could be done right now, right? And I could be like, okay, cool, solve this, this is your answer. But wait. Oh, wait. There's one more thing that you don't want to miss, which is that it's each year. Okay, this is per month and this is for the year. It's asking for the year. So don't miss this because you might lose points. All right, make sure you know what it's asking for and multiply this because how many months are there in a year? 12. So multiply this by 12. And then if you solve it, and let me just double check. 12 to Yep. Okay. So if you solve this, it should be 1.8 times 10 to the 2 grams of chlorine, oh well, chlorine per year. Cool? Cool. All right, so sorry. I'm just gonna solve this with a tiny bit of algebra. Um, because this is more logic, this question actually. It kind of tests if you know what it's talking about, all right? So let's see. It contains this much Cl by mass, right? So here is the formula. Remember, for the empirical formula stuff, you don't want to use the percentages, you don't want to use mass, you want to use moles, right? So, let's convert this into moles first of all. So Cl3, right? So 3 times what is Cl? Cl is 35.45. That's the atomic mass, right? Now this is equal to, give me a second, 106.35 grams per mole. All right. So here's the deal, right? So we know that this number, right? Well, let's just do like a hypothetical, right? So Cl3 over, well, the mass of, right? Let's just put that there so you know what we're talking about, right? The mass of Cl3 over the mass of M plus Cl3 is equal to 0.6557, right? Because remember, when the percentage, you have to actually move the decimal point too, right? So, basically, um, it's saying that out of this, right, out of this molecule, chlorine makes up this much of it, right? So chlorine out of this molecule makes up this much of it, right? So that's how you would write that out. Now, what we're solving for is this right here. We're solving for M, right? So let's do a bit of math, right? Let's take this value we got here and sub it in. All right. So we got 106.35 over M plus 106.35 is equal to 0.6557. All right, let's do a bit of algebra. 106.35 over 0.6557 is equal to M plus 106.35, right? And then we just subtract this from both sides, and that would get us 106.35 over 0.6557 minus 106.35 is equal to M, right? Now, if you solve this, M is going to be equal to a mass of about, what was it, like 55.8 something? I think it was like 84 or 85. I'll just say 55.85. Because I did the calculation earlier. I forgot what number I got, but I know what the answer is, right? Because this is the answer basically when you solve this. So now this is going to be the mass of M, right? So let's find which one has that mass. So we can kind of follow it up. Oh, guess what? It's iron. So M is iron. Whoa. Whoa. Okay, that's the answer. All right, so for this one, another straightforward one, kind of. You just gotta know what you're doing, right? So it gives us estradiol, right? And it says as the mass percent composition of carbon making this much, hydrogen making this much, and oxygen making this much. Now you're told to find the molar mass, right? Sorry, you're trying to find the molecular formula with this molar mass, right? So we can find the empirical formula, uh, and then what we do with that, oh, formula, just formula. And then what we do with that is we find out how much this is the ratio between the empirical and this, and that's going to give us our molecular, right? So basically, to find the empirical formula, first of all, we got to know how many moles of each atom are in the empirical formula, right? So here's the thing. We need to find the moles, but this says mass. So it's going to be in grams, right? So I know these are percentages, but what I would recommend for this problem is just multiply them by 100, right? So basically just leave them as is, but make them grams. If you multiply all of these by 100 grams, it should give you the exact same numbers, right? Or you can multiply by 10, 1, any number really. But I'm just going to be doing it by 100 so that the numbers stay the same, right? Because in reality, this percentage is 0.7937, right? So if you multiply by 100, you move the decimal point 2 back, and then it becomes the exact same number, right? So here, let me write it out so it'll make more sense. So first, let's find carbon, right? So carbon is 79.37 grams because we're multiplying by 100, right? Now, here, times 100 grams, and then times 100 grams, and then times 100 grams, right? So, this is in grams, and we're gonna multiply it by something to get us the moles, right? So 1 mole, over what's the, what is the atomic mass of carbon? It's gonna be 12.01 grams, right? 12.1 grams per mole, or moles per gram. 1 mole per 12 point grams, right? So this is gonna give us 6.609 moles of carbon, right? Now we take hydrogens, which is 8.88 grams, right? Multiply that by 1 mole over 1.01 grams, right? This is equal to 8.792 moles of hydrogen. And then for oxygen, we're going to take 11.75 grams and multiply that by 1 mole over what's actually 16, right? Grams per mole. And that is going to give us 0.7344 moles of oxygen, right? So now we have the moles of each. Whoops. Well, sorry. Now we have the moles of each, right? But what we got to do now is we got to find the ratios between them. So we're going to find whichever one's the smallest one, which happens to be this one, right? And divide all of them, right? So then this one is going to be 6.609 divided by 0.7344. This one is also going to be 8.792 divided by 0.7344. And again, just as a formality, we'll divide this by 0.7344. We all know it's going to be 1, but just so that we can see it, right? Which is going to be the first one is going to be 9, second one's going to be 12, and this one's going to just be 1. Right? So now we know that that's going to be the ratio for each of these, right? Now, here's the thing though. We can already write out the empirical formula just like this. C9H12O, right? But this is not the answer, okay? What it's asking us to find is the molecular formula. So we know that like the molecular formula has this atomic mass, right? So first, let's find the atomic mass of this, the one we just made, right? So to find the atomic mass of this, we can multiply each of the moles of each atom by their atomic weight, right? So we're gonna do 9 carbon atoms times 12.01 grams per mole, right? Plus 12 hydrogen atoms times 1.01 grams per mole. And then we're gonna add on 1 oxygen atom times 16 grams per mole, right? And what is that going to get us? That's going to get us 136.21 grams per mole, right? So the thing is, we know that this one has this many grams per mole, right? But the one we're trying to get to is this many grams per mole. So what are we going to do? We are going to divide it. So let's do some math. 2 points, sorry, not 272.37 over 136.21, right? This is going to be about 2, right? I think, I don't know the exact numbers, but it's about 2. So what that means is that this times 2 is going to make that molecular mass, or sorry, that molar mass, right? So what that means is we have to multiply this entire thing by 2 to get our final answer. So when we do that, we get C18, H24, and O2, and that is our final answer. So I followed a little different method than the answer key for this one, but I got the right answer, and it's what made sense to me. All right, so we have these two, right? And what it says is we start off with 4.3 of all of this. Now this is just a coefficient for this. I know waters of hydration, right? Blah blah blah. That's like a lot of fancy terminology. All it's basically asking is this is a coefficient for this, right? So if this was 2, then this whole thing would be multiplied by 2, right? Or 3, right? Like that. So basically, what you got to do is you got to find out. Well, first of all, let's find out how much of each there are, right? So it's a 4.3 gram sample, right, of Epsom salts, right? So this total is 4.93. This plus this, right? Here's the thing though. The mass of the sample after complete dehydration. What does dehydration mean? That means we got rid of the water. So we get rid of the water. This is just 2.41 grams, right? So if this is 2.41 and the total is 4.93, then how do we find how much water there was, right? Well, it's simple. It's just 4.93 minus 2.41. So let's do that. 4.93 grams. Sorry, 4.93 grams minus 2.41 grams, right, of how much MgSO4 there was, and then that gives us how many. I have it written somewhere. All right, that gives us 2.52 grams of water, right? H2O. So in the original formula, there was this many grams of this and this many grams of this. So what can we figure out from that? Well, first of all, we need to figure out the ratio, right? Because we're just trying to find the ratio between this and this, right? If it's a 1-to-1 ratio, then x is just going to be 1, right? And if it's like 2, then it's going to be 2, right? Or 3, right? So we're trying to find out how many of these there were. So to do anything with ratios, again, we got to convert it into from mass to how many moles of each atom there are, right? So again, we're going to use atomic mass for MgSO4. What we're going to do is we're going to take 1 times an Mg molecule. Oh, well, right, which is 24.31 moles per gram. Sorry, grams per mole. Um, and then, wait, give me a second. Yeah. So, sorry, no, what, okay. Let me step back for a second. This is in grams, right? These two values are in grams, right? But what we have here is moles of each. We know this is 1 mole, this is 4, this is 1 of this, right? This is 2, 1, right? So we have to convert this from moles into grams. So that's what we're doing, actually. So we're taking this and we're doing 1 mole and then 24.31 grams per mole, right? Plus one S atom, times 32.07 grams per mole. And then we're going to have 4 oxygen atoms. Each one is 16 grams per mole. That gives us 120.38. Right? And then for H2O, we're going to do 2 hydrogens. Each one is 1.01. And then we're going to do 1 oxygen, which is 16. Right? And that is going to give us 18.02 grams. Right? So now we have the grams of each of these in just on their own, right? But here's the thing. In this equation, we have this many grams of this and this many grams of this, right? So the ratio between this to this, we have to find that out. So how are we going to find that out? Just simple division, right? So, let's bring this over here and do 2.52 divided by 2.41. Let's see that ratio between the two of them. And that is going to be 1.04564 blah blah blah, right? And now what we're going to do is so this is the ratio to get from the amount of water we have to the amount of sorry, what was I gonna say? Oh yeah, so this times 1.04 is how many grams of water we have, right? So the amount of grams of this times 1.04 is how many grams of this we have. That's what we just calculated, right? So let's do the same thing here to figure out how many grams of water we should have, right? Because we don't know how many grams of water we have. It's X. It could be anything, right? So let's take this and do that same calculation. Multiply this times 1.04, blah, blah, blah. Let me type it into my calculator. And that's going to give us 125.87, whatever, some decimal, right? So here's what we're going to do with that. What we're going to do is we're going to take this, because now we know that this is how many grams we should have in the original, right? We found the ratio. We found using that to how much we know we have, because remember, this doesn't change from the before and after, but this does. So this is how much water we should have, and this is how much is in each one. So if this one is how much we should have, and this one is each one, how do we find out what we multiply this by, right? Simple. We just take this and divide that. So we're gonna take 125.87 and divide 18.02 grams of water, right? Because this is water, the top is water, the bottom is water. And what that should give us is about 6.98 blah, blah, or 7, right? So really it's 7. Because 6.98 rounded, that becomes 7. So the answer is that there's 7 here, right? Because when you take 1 of this and 7 of this, it creates the same ratio as this to this, right? And yeah. All right. So for this one, you just kind of need to understand what's going on and you'll get it. Right. So for this one, first of all, there's a correction. If this is the reason you got it wrong, it's not -3, it's -2, right? For this, to match up with the answer key, I guess there was just a typo in the question. Anyways, that's not important. Let's solve it. So we know that this molecule, right? There's 2.395 grams of this, right? And it contains this many moles of Cl specifically. So what we want to find is this. M is not an actual atom. I mean, it is, but we don't know what it is. It's just a variable, right? So we know that the total is this many grams, and we know that this is how many Cl moles there are. So if we want to find how many grams of M there are, right? We take the total, well, total, and subtract the grams of Cl, right? So how do we find the grams of Cl? Well, let's use some math. So let's start off with 3.606 times 10 to the -2 moles, right, of Cl. Now, how do we cancel out moles? We put moles on the bottom, 1 mole, and we multiply by the atomic mass of Cl. Where is that? That's 35.45 grams per mole, right? Now, what that is going to give us is 0.127, sorry, this is going to give us 1.2078, oh my gosh, 278 grams of Cl, right? There we go, pretty straightforward. This is how many grams of Cl there are, right? Now, what we need to do is we need to take this, which is the total, and subtract this, right? So simple, 395 minus 1.278, right? How many grams of M are there going to be? There's going to be 1.117 grams of M, right? All right. So we're trying to find the atomic mass of M, right? Which is basically what we're trying to say is like on the periodic table, what would the atomic mass be? We don't really know what M is, but what is the equation? So here's the thing, we gotta do a bit of algebra, right? We have this number, which is the grams of M, right? So let's do a bit of algebra, which is 1.117 grams of M, right? And now how do we technically reach that number? Well, what we gotta do is we gotta take the moles of M, right? And multiply it by the atomic mass of M, right? Which is what we're trying to find. So we take the moles of M and then we multiply it by the atomic mass of M, which is X. That's really what we're trying to find, right? So let's take this. How many moles of M are there? Well, here's the thing. We know that there's 3 Cl's for every 1 M, right? So we know that there's this many moles of Cl. So then to find the M, we just divide this by 3, right? Pretty straightforward. So let me subtract this. I mean, let me erase this and let's just replace this with 3.606 times 10 to the -2 over so that's what this is, right? And we're dividing it by 3, right? So we're taking this, dividing it by 3. And now in terms of algebra, we just divide both sides. You know, this equation becomes 1.117 divided by, well, whatever this giant number is, 3.606 times 10 to the -2 over 3, right? And that is equal to X. You know, you do all the calculations. I'll just skip ahead and say there's 92.9 grams per mole for X. That is the atomic mass of X. Now you could take this to the periodic table and look it up, blah, blah, blah. But for this answer, all we need is the atomic mass. So that's what it is. And yeah. All right. So for this question, we're going to need to find out in a rock, right? This is our rock. Okay. And this rock, this much is lead. Okay, this percentage, right? and what we need total is this much lead. Okay, whoa, that's a lot of lead. All right, so we're gonna say how much do we have to multiply this rock by to get that much lead total, right? What's the first step? First, we gotta find out how much lead is in each rock, right? So we know that in a certain rock, 38% of it is this molecule, 25% is this molecule, and 17.4% is this molecule, right? But this doesn't tell us the lead, this tells us the molecule. So first of all, let's find out how much lead is inside each molecule, right? What is that? That's just basically mass percent composition, right? That's all it is. So we got to take this and, well, we got to find out, we got to use atomic mass to find out how much lead is in each one. So, wow, I really gave myself no space for this problem. All right, let's start. So we got to take 1 times the mass of lead, which is 207.2. And we'll divide that by 1 times 207.2 plus the sulfur, which is 1 sulfur atom, right? Times 37, I think. Yeah, no, 32.07, right? And this is going to give us what percent? It's going to give us 0.866, right? Which is 86%, right? So then we're going to do the same thing for the other two atoms. We're going to take 1 times 207.2, right? And we're going to divide that by, again, 1.207.2 plus how many carbon atoms are there? There's 1. So 1 times 12.01, right? Plus how many oxygen atoms are there? There's 3, so it's going to be 3 times 16, right? And that is going to give us a decimal of 7754, so 77%, right? And then for the third one, for lead 2 sulfate, we have, again, just one lead atom, right? Over that same 1 lead atom, plus 1 sulfur atom, which is 32.07, plus how many how many oxygens are there? 4, right? 4 times 16, right? And this is going to give us a fraction or decimal of 0.6832. So 68.32%, right? So now we have the percentages of how much lead how much lead is in each of these molecules, right? So 86% of this is lead, and 77% of this is lead, and 68% of this is lead, right? Now, here's the thing. Now to find the lead in the total rock, we're going to take these percentages, and we're going to multiply them by the total percentages. Okay, so here's what we're gonna do. Actually, so if we take these percentages, right, and we multiply them by 100, we can get how much lead is in 100 grams of each. And that's going to make it a little easier. That's going to give us better numbers to work with. So let's move the decimal place down for all of these. As long as we do it for all of them, the ratios should stay the same. So, and then we're going to multiply it by the percentage on the rock, right? So let's say we have 100 grams of the rock. That's why we're multiplying each of these by 100, right? We have 100 grams of the rock. How much of each of these are we going to have? Right? So let's take this and say 86.6, and we're gonna multiply that by how much? 38%, right? And then we're gonna add 25. Sorry, we're gonna add on 77.54. Multiply that by how much percent? 0.25 or 25%, right? And then we're gonna take the last one, which is 68.32, and multiply that by how much percent? 17.4, or sorry, 0.174, right? And what this is going to give us is um let's see. I believe 64.18 grams, right, of lead. So basically what this is saying is that if we had 100 grams of a rock, right? If you had 100 grams of a rock, then out of that, 64.18% would be lead, right? Which is perfect. So that's exactly what we're looking for. Now we have the big rock, and we know that this is 64.18%, right? Now, what we got to find, and the reason I'm just making this a percentage is because this is out of 100 grams, right? Um, and so it's divided by 100 technically, right? So anyways, so that percentage, right? What we can do is now that we know that, we got to take that and we got to just use a bit of dimensional analysis to get to our final answer, right? So here I am gonna go right over here since I literally gave myself no space for this question. Um, let's do 5.0 metric tons, right? This is what we have, or what we're trying to get to, right? We multiply this by what? Now we want to turn this into kilograms, right? So what did they say the conversion factor was? 100 kilograms, right? So 100, I'm sorry, 1,000. 1,000 kilograms for 1 metric ton. And this gets canceled, right? Now, wait, but that's not it. That's our conversion factor. Now we need to multiply this by the how much is going to be lead, right? Well, here's the thing. So we need to make sure that our units cancel, right? So this is 1,000 kilograms of lead, right? That's what we're looking for, 1,000 kilograms of lead. So on the bottom, what we're gonna put is the lead, right? So we're gonna put 64.18 grams of lead on the bottom. That way these cancel out. Oh, sorry. Here's the thing. It's technically 100 grams over 64.18 grams, but since this is a percentage, this could also be 100 kilograms, and this could be 64.18 kilograms per 100 kilograms, right? This is just a percentage. This could literally be anything. So for this, what we're gonna do is we're gonna make them both kilograms. So kilogram, kilogram, right? And then this is the lead. At the bottom, this is the lead, and at the top, this is the total, right? So cancel, cancel, right? What we end up with is 7.8 times 10 to the 3 kilograms. And that is our final answer. All right, and then to end our time, let's end with an easy problem. This is pretty straightforward. And if you've been following the math so far for all of these questions, it should be really easy. All right, this is the statement, right? We have to correct what the problem is. So it's saying this says that there's 3 grams of hydrogen for each gram of nitrogen, right? Why is that wrong? Well, obviously this isn't talking about mass. This is mass. And this is number of atoms, right? So this isn't saying that this is 3 grams. It's saying there's 3 atoms of nitrogen to each gram of nitrogen. So if we really want to change this, we just remove this, say atoms, remove this, and say atoms. And yep, that's your explanation.